My name is Lea. I am a museum educator at the National World War II Museum. Today we're going to be doing a really fun chemistry experiment in our kitchen. We're going to learn all about pH. So before we get started with our really fun activity, first we're going to talk about pH, what it is, and why it's important. So have you ever gotten a sore mouth from eating way too much sour candy? Or have you gone swimming in a local swimming pool and opened your eyes under the water and it kind of burns your eyes a little bit? So what you're experiencing in both of those cases is pH. So pH is essentially the measure of how acidic or basic something is. So why is that important? So it turns out pH is important in many aspects of daily life and science. So when you're baking, it's going to be why your cakes and your cookies rise. In environmental science, it's going to be how we can tell whether or not soils are healthy for plants or whether or not oceans or other natural bodies of water are healthy for the fish that live in them. It's going to be why Drano can unclog your drain, and it's going to be why your stomach can digest your food. So let's take a look here at a pH scale. All right, so what we're looking at here is our pH scale. So as you can see at the bottom here, it's going to go from 0 to 14. There are actually things that can fall below 0 or above 14, but they're very uncommon. So we're actually just going to look at 0 to 14. What's really interesting about the pH scale is that neutral is actually in the middle of the scale. So 7 is going to be what we consider to be neutral. It's neither acidic nor basic. As we go below 7, as our numbers get smaller, that's actually going to be more acidic. And then as we go higher above 7, it's going to be more basic or alkaline. So something that is a 0 and something that is a 14 is actually going to be equally as reactive and powerful. But just in different ways, whereas things in the middle are going to be our neutral. So let's look at some examples from our everyday lives. So an example of something that's neutral is going to be pure water. So that's not acidic, it's not basic, it's just pure. So that is neutral. As we go towards our acidic side, some things you may already be familiar with that are acids. We have our lemons and limes, oranges, things that are citrus, have citric acid in them. So those are acidic. We have vinegar, so anything that's pickles or anything like that are going to be acidic. We have sodas, we have sour candies. Things that are strong acids are things like gastric acid, so the acid in your stomach, or battery acid. Looking on the other end of the scale, things that are some weak bases, we have baking soda, toothpaste, things like that. A lot of our soaps and detergents are also bases. Whereas Drano and bleach are going to be some really strong bases. So what exactly is pH? So pH we can think of as standing for the power of hydrogen. So hydrogen is going to have everything to do with what pH means. So pH is essentially sort of a shorthand for the concentration or the amount of hydrogen ions in a solution. So what is an ion? So an ion is a positive or negatively charged molecule or atom. So how might those be formed? So let's take a look at an example. In our webinar on the Manhattan Project, we learned a little bit about water and the subatomic particles that make up water. We learned that water is made up of 2 hydrogen atoms and 1 oxygen atom. And these atoms are bonded together through their electrons. So our electrons are negatively charged particles, and the hydrogen and the oxygen share those electrons and are bonded together. So when they form the molecule water, then all the electrons, those negatively charged particles, are going to kind of gather together on the oxygen side and make the oxygen side of the water a little bit slightly negatively charged. So then that's going to leave our hydrogen that has now the proton in the middle and its nucleus. That positively charged particle is going to make the hydrogen sides more positively charged. So if it comes into contact, if it meets another water molecule, then the positively charged hydrogen on the first water molecule is going to be weakly attracted to the negative side, the negative oxygen on the new water molecule. So they're going to bond together. That positive and the negative are going to be attracted to each other, and they're going to form a weak bond. Now, sometimes that bond can be so strong that the new water molecule is actually going to pull over that hydrogen over to itself. So what's interesting here is that you'll notice that original water molecule now is kind of broken into two pieces. And what's left is what's called the hydroxide. So that is going to be a negative ion. So it's negative because you can see when the hydrogen hops over to the new water molecule, it actually leaves behind its electron. So this red electron right here, it's being left behind. So because the electrons are negatively charged, since we added or we left behind that negatively charged particle, that makes the hydroxide a negative ion, okay? So then we can look at our new water molecule that received that hydrogen ion, which actually now is only just the proton because it left behind its electron, so it's just our proton. Our protons are going to be positively charged. And so now this new water molecule with its new hydrogen, positive hydrogen ion, is now going to be known as hydronium, and that's going to be a positive ion, okay? So for simplicity, we're going to just get rid of that extra water molecule, and we're just going to look at the two pieces that we have here. So we have our hydroxide, which is negative with that extra electron, and then we have our hydrogen ion, which is the hydrogen without its electron, just its proton, the hydrogen ion, okay? So pH is measuring the concentration or amount of that positive hydrogen ion, so that one you see on the right. So it's measuring the hydrogen ions in a solution. So what is our unit of measure when we're talking about these hydrogen ions? So hydrogen ions are measured in a concentration, a unit of measure called moles per liter. So liters are about 1/4 of a gallon. But what is a mole? So a mole is a unit of measurement which is equal to about 600 sextillion molecules or ions. So this sounds like a lot, but molecules or ions are very, very tiny. So a mole is still very, very small. It turns out that water has about 0.0000001 moles per liter. This is a very, very tiny amount. So since this number is a bit ridiculous, a mole is a bit ridiculous, we're gonna just write it in a shorthand. So 0.0000001 moles per liter can actually be written in a shorthand that looks like 1 × 10 to the -7. So we get this -7 because we have, you know, 7 numbers or 7 decimal places to the right of the decimal point. So 0.0000001 is equal to 1 × 10 to the -7th power. So pH is going to simplify that even more, and it's just going to take this little number up here. It's just going to take this little baby number 7. It's going to make it positive and just take that. So pH 7 is basically just representative of the amount of hydrogen ions. It's just saying that per liter, water has 0.0000001 moles per liter in it. But we don't want to say that every time, so we just simplify it and we say it has a pH of 7. Okay, so let's take a look at another example. If we go all the way down the acidic side of the scale to gastric acid, that's our stomach acid, that has actually much more, about 1 million times more hydrogen ions in it per liter. So that is a little bit of an easier number to look at, 0.1. It's closer to 1 moles per liter. So that can be written as 1 × 10 to the -1st power. Again, we're going to simplify that by taking this small number up here, we're going to make it positive, and we're going to have pH of 1. So now we're going to go to the entirely other side. We're going to go look at Drano. This has a very tiny amount, a very tiny amount of hydrogen ions in it. It has 0.13 zeros and a 1 moles per liter. So again, I don't want to write that every single time, so we can write it and a shorthand of 1 times 10 to the negative 14th, because we have 13 zeros and then a 1, so that's 14. Again, it's a smaller number. The numbers are below 1, so it's a negative. So the pH is going to take that tiny number, that 14, a negative 14, we're going to make it positive, and that's going to be our pH. So it's really just a shorthand for these kind of ridiculously tiny numbers, just to make it easier. It's representative of those numbers. So, okay, so now we understand what the numbers kind of mean, but why is 7, why is neutral in the middle? It's not the solution with the most hydrogen ions, and it's not the solution with the least hydrogen ions, so why is it neutral? Okay, so to answer that question, we're going to circle back to how our hydrogen ions are formed. So we remember that we had our hydrogen ion, which was positive, but we also had our buddy, the negative ion, the hydroxide. So whether or not something is acidic or neutral or basic is going to depend on whether or not the amounts of these two ions are equal. Okay, so in water has 0.000001 moles per liter hydrogen ions, and it also has 0.000001 moles per liter of hydroxide. So they're actually equal, okay? So since they're equal, our positives and our negatives are equal, they balance out, and that makes it neutral. So neutral is in the middle. Now, if we go towards the acidic side, we get more hydrogen ions and fewer hydroxide ions. So now the balance is off, and because of that, it becomes acidic or more reactive, okay? So then if we go the other side, now we have fewer hydrogen ions and more hydroxide ions. And again, the balance is off, but in the other way. And that also makes it more reactive. So now we have a base, okay? So to sum up, pH, the numbers are essentially our shorthand for the concentration of these hydrogen ions. And whether or not it's an acid or a base is going to depend on if those hydrogen and those hydroxide ions are equal. Acids are going to have more hydrogen ions, and bases are going to have less, okay? So one of my favorite things about pH is these things called pH indicators. So pH indicators are really cool chemicals that change color depending on if they come into contact with an acid or a base. So one that you may experience in school is called litmus paper. So it's a special kind of paper that's going to change color whether or not it's in an acid or a base. But there are also natural pH indicators. So some examples are beets, red onions, blueberries, curry powder, and red cabbage. So my favorite one, and the one we're going to be doing today, is red cabbage, because red cabbage it changes a wide range of colors. Some of these pH indicators only change 1 or 2 colors. Red cabbage is going to change a wide range of colors. Okay, so you can see in the center here, red cabbage juice in a neutral environment is going to be sort of this purpley blue color at that 7. As we add an acid to it, it's going to turn purple and red and pink, and if we add some bases to it, then it'll turn blue and green. So it's really pretty. So if you want to make your own pH indicator using a red cabbage, it's super simple. You just need a red cabbage, a pot to boil some water, and a strainer. So today what we're going to be doing is we're going to be testing these 5 household ingredients that I found around my house. So we have some tap water that we're going to be testing, a lemon, some bleach, some sparkling water, and some baking soda. First, what we're going to do is we're going to watch a video about how to make your own cabbage juice. All right, so the first thing you're going to do is you're just going to chop up your cabbage loosely. And you're going to stick it in a pot of water, make sure it's full. Stick it on the stove and bring it to a boil. Once your cabbage is boiling, you're going to turn off the water and let it kind of marinate and sit there for a while until it cools off. Once it's cooler, you'll bring it over to your sink and you're going to strain out those cabbage leaves. So you're going to pour the water into another bowl and strain out the leaves so you're left with just the liquid there. So you can see we've kind of taken out some of the color, that red color, and we're left with the juice. Okay, cool. So, okay, we can now start our experiment now that we've prepared our juice. So you can see I have my 5 cups here lined up. They have our cabbage juice in it. I've also printed out my pH scale, so when we pour some stuff in there, we can check out what relative pH. It's not going to be precise, but it's going to give us a ballpark idea of the pH of our substances. Okay, so scoot back a little. Okay, so let's start with our lemon. Okay, so based off of what you guys know about lemons, before I pour this in, I want you guys to make a hypothesis or a prediction of what color you think this is going to change. So looking at our scale, do we think lemons are going to be more pink? Are they super acidic? Or are they basic? Are they going to turn more blue and green? Okay, so let's find out. I'm going to pour it in. All right, hopefully y'all can see this. So it actually turned a very bright pink. So if we're looking on here and we want to match it, it's going to fall actually pretty perfectly under the pH of 2 or 3 down here, which actually does match what we know about lemon juice. Lemon juice is a strong acid. It's very acidic. And so it turned our lovely cabbage juice a nice color. All right, so the next thing I'm going to look at is I'm going to look at my sparkling water. What do y'all think? It's water, but you know, it has carbonation in it, and it also has some flavors. I think the one I have is actually lime flavored. Excuse me. So we're going to try this out and see what color it changes. All right. Okay, so that has turned sort of a light purple color. All right, so looking at my scale here, it actually looks like it's about at a 5 or a 6 on our scale. So it's still acidic. It's below 7, right? So it's below 7, so it's still acidic. But it's not as acidic as our lemon juice. It's kind of it's a mild acid thing. Okay, so let's check out our tap water. Tap water, again, is not pure water. So we're gonna see if we think it's basic or acidic, or if it is neutral. So here's our water glass. Pour that in. All right, so it did change a little bit of a color. It's not as purple as when it originally started. We can kind of compare, you know. So it actually fell, it's a little bit bluer, so it did fall in the 8 or 9 category, which checks out. Tap water is usually made to be a bit more basic, especially here in New Orleans, which is where we are. They do make the water more basic so that it doesn't leach out as many metals from the pipes that the water is running through. All right, cool. All righty, so the fourth one we're gonna look at, we're gonna look at baking soda. So I actually mixed some baking soda in with some water just to make it easier. So let's see what color that changes. All right, so that has changed a really pretty green. So let's take a look at our scale here. So that has fallen a little bit more down the base side as well. You know, it's not super precise, so I can't really tell, maybe between a 9 and a 10 or so. But we do know it's a base. It's it kind of came out as a base. All right, so the last thing I'm gonna do, so I'm going to use some bleach. So I have a little tiny bit of bleach mixed with some water in here. So we'll see what color it changes. All right, so that has changed our water to be a very light yellow. So that checks out because we know bleach to be a really, really strong base, right? So we're over here almost off of this scale because this is a bit green and that's even lighter than that. So we can see from this that bleach is a really, really strong base. All right, so now that we've gotten to try some things out at home, I want you guys to, you know, try out, make your own pH indicator, test out some things around you. see what they are. Do they match your predictions? Is something acidic that surprises you? Is something a base that you didn't know was a base? So yeah, try it out at home. We're gonna end here with looking at how this is relevant to World War II. So in World War II, as we all know, a lot of things were rationed during World War II. So families and people were really, really encouraged to grow and preserve their own foods. As you can see, a lot of these propaganda posters were around encouraging people to grow their own foods and to can things. So pH is really, really important in canning. So there are two methods of canning. There's water bath canning, and then there's pressure canning. And whichever method you're going to use is going to be dependent on the pH of whatever it is that you're trying to preserve or can. So water bath canning is much simpler. You basically just submerge your cans in boiling water. It's much simpler, it's much less expensive, less complicated. When you go to pressure canning, you're going to need a specific device for pressure canning. So it's much more expensive. During the war, so these were made of aluminum back then, and aluminum was rationed at that time. So actually these pressure canners were rationed, and people were encouraged to share pressure canners, you know, within their families and neighborhoods. And they were also a little bit more dangerous. They were known to explode because they have to bring up the pressure inside to such a high pressure that it could explode if it malfunctioned. So the way these things work, water bath canning is just using, you know, it's bringing it up to the temperature of boiling water. And it's using boiling water and then the acid, because the acid in the fruit or the vegetables that you're canning, to kill the bacteria. For pressure canning, you need to use pressure canning for anything that has a pH of 4.6 or above. So anything that isn't very strongly acidic, you have to use pressure canning. Anything that is more acidic, the acid itself, along with the heat, is able to kill the harmful bacteria. But anything above that, the heat alone and the acid alone is not enough to kill it. So you need to bring it, the pressure canning is going to bring it to a much higher temperature in order to kill that harmful bacteria. Okay, so there are a couple of ways that you can actually bring down the pH of a food to make it easier to preserve. One of those ways is pickling. So we have put together a recipe for you guys. If you want to try pickling at home, you don't need to can these. These are good in the fridge for up to a month. Okay. Alrighty, so let's take a look at some questions. Okay, alrighty. So one of our questions is why red cabbage? Can I use normal cabbage? Can I use green cabbage? No, you cannot use green cabbage. You have to use red cabbage. So red cabbage has a chemical in it called an anthocyanin, and that particular chemical, it's also found in blueberries and red and purple grapes. It's that particular chemical that you're leaching out, and that's what you're using as the pH indicator. Okay, so somebody asked, don't neutrons have a neutral charge and negative charge are electrons? Yes, that is true. So neutrons are the neutral charge and the negative charge are electrons. So within an atom, the number of protons, so neutrons are neutral, right? So the overall charge of an atom or an ion is going to be basically the balance between the protons and the electrons. So when we're looking at our hydronium, when we're looking at our hydroxide, the negative ion, if you counted up all the protons and the electrons, because it kept that electron from the hydrogen that left, it now has one more electron. So all the other electrons and protons cancel each other out, but it has an extra electron, which makes that negative. And then in the hydrogen actually doesn't have a neutron, it just has a proton, and it lost its electron. So since it doesn't have an electron to balance out the proton, then it's a positive charge. So hopefully that helps. Okay, yes, okay, so Ava wants to know if you can use red onion, and yes, you can. So that doesn't have as wide of a range. If you check out our PDF on using cabbage juice as A pH indicator, we have a really cool graphic in there actually that shows some of these other natural indicators in the range of colors. Red onion is on there and it does change, I think, a couple different colors, but not as wide of a range. But yeah, definitely please still try it out and send us photos. I would love to see how it works. Okay, so one other question, what made aluminum the ideal metal for cans at that time? Okay, so aluminum is a type of metal that is actually very resistant to corrosion. It's a metal that's not going to rust. It can easily support different like pressure from carbonation that was required to package things like soda, and it was really it was strong enough to withstand pressure from pressure cans and stuff like that. All right, so I think that's all the questions we have for today. Thank you guys so much. If you guys end up making any pickles or testing out anything, please send us videos on Flipgrid or send us some photos. We would love to see your guys' experiments and your learning. All right, thank you so much for joining today, guys. See you later.